Hello everyone. Today we are going to be looking at diagonalization. So let's start with the definition. An n cross n matrix A is diagonalizable if there is a diagonal matrix D such that this matrix A is similar to D. Remember in a previous video session on our characteristic equations, we talked about similar matrices, and that's what we are looking at. A is it's D, not B, guys. Okay, what does that mean? If I say A is diagonalizable, that means A is similar to D. That definition of similarity says if there is an invertible matrix P such that D equals P inverse AP. Now, diagonalizable matrices have a very close connection to eigenvalues and eigenvectors. So let's start with a very simple example of saying whether a matrix is diagonalizable or not. Now, remember when we say that a matrix is diagonalizable, what does that mean? If I say, given this, we want to prove A is diagonalizable. It means this matrix D can be written as P inverse AP. Remember, what does this imply? This implies that A is similar to D. Now, much more better to do PD equals AP than doing all multiplication of these three matrices. Much more easy to do it in this form. So what if it is diagonalizable? That means as we are given all these three matrices, we just have to plug and chug them out. So P times D gives the matrix 4 minus 3, 4, 2. A times P, that is, gives us the same matrix, which was PD. So clearly from the above theorem, we see that A is diagonalizable. And also, let's look at some of the facts. As A is similar to D, in Theorem A and our section 5-2 on characteristic equations, that means if a matrix is similar, they will have the same eigenvalues. So D is the diagonal matrix. Remember what's my D here? My D here is, if I write, what is it? 4, 0, 0, minus 1. Okay, so D is a diagonal matrix, and we all know that if it is a triangular matrix. So if you have a triangular matrix, then the eigenvalues are on the main diagonal. So instead of solving this matrix A and finding the eigenvalues, if we know it is similar to another matrix D, we just need to look at the eigenvalues of D, and they will be automatically the eigenvalues for A. So from that theory, we say eigenvalues of A are 4 and minus 1. A very important result if a matrix is diagonalizable, and that is, if matrix is diagonalizable, there exists a diagonal matrix such that D equals P inverse AP. What is the main result is that suppose I want to find powers of this matrix A, suppose A to the power 100, or say A to the power 5. Let's start with A to the power 5. So what I have to do is just find the diagonal, just find the invertible matrix, and simply just take the powers of 5. Suppose I want to find A5. What does that mean? There won't be much computation because it is going to be simply D to the 5. Everything else is just simple, easily multiplicable. Instead of doing A5, A times A times A times A 5 times. This is more easy to do. Okay, so we can avoid a large amounts of computation. So let's take an example. We are given this matrix A, P, and D, the same matrix we just saw earlier. So if I want to find A square, what I'm going to do is I already know my matrix P. I find its inverse. We all know how to do that. We have done it many times, guys, now. And then D square, more easy. 4 square, 1 square, we already know is 1. And when you just multiply, you get the answer this. Now A to the power 4. What is it? These are the answers I'm writing down, guys, for you. So this is simply the beauty of using diagonalizable matrices if you want to find in terms of higher powers of this matrix. Let's look at an important aspect is suppose now here we were given matrices where we were given an A, D, and P. We just had to prove that that matrix is diagonalizable just by doing matrix multiplication. But the real part is, if I'm given a matrix, I like to know whether it is diagonalizable or not. If it is, awesome. If it is diagonalizable, okay, we have to prove certain things. So that's one of the biggest theorems we talk here is that a square matrix is diagonalizable if and only if A has n linearly independent eigenvectors. Look at the fact. The size of the matrix also has a very important role. I have a size n, okay? Then if it is diagonalizable, it has connection to eigenvectors, and the number of eigenvectors has to be exactly the same as the size. And not only that, we also have to have the fact it is linearly independent. Notice we are going back to our beginning of this eigenvector section 5.1. Linear independence, and the size, we are all going back to chapter 1. So notice every time we are going back to our basics. Okay, so if I say my matrix is diagonalizable, that means can I find n linearly independent vectors? The question is, how can we get those linearly independent vectors? Those linearly independent, remember now vectors are nothing but the columns of that invertible matrix P. So when we have this scenario, so we say that A is diagonalizable, that means A can be written as P times D times P inverse, where D is a diagonal matrix and P is the matrix consisting of all the eigenvectors corresponding to those eigenvalues. So the idea is the diagonal entries of D will give the eigenvalues of A, which will be corresponding to the eigenvectors in P in the same order. This is going to become more easy for us, but remember the basic. Basic is, I say a matrix is diagonalizable. Look at the size, and on that size, if it has exactly the same number of linearly independent eigenvectors, that's what we have to do. Okay, so let's start with an example. We want to say find a matrix P that diagonalizes A. I'm going to go back to our notes, which I have done earlier, and that's where I'm basically getting all the material from. So we had this matrix. I did an example in this matrix and characteristic equation in section 5.2, and also it's given in detail in page 8 on that lecture notes, and they have been posted, guys. So when we looked at this matrix 5-3-3-5, we found the eigenvalues were 8 and 2, and we found the eigenvectors corresponding to lambda equal to 8 to be x1, 1, and 1. That means, remember, there are infinite eigenvectors corresponding to an eigenvalue. And similarly, there are infinite, and so we just need one of them. We just need one eigenvector, guys. So we can say, make our life simple, say x1 is 1. Remember, x1 is a scalar here. So for lambda equal to 8, we are picking up this eigenvector 1 and 1. Let's look at an eigenvector which corresponds to lambda equals 2. It is x2 times minus 1 and 1. Again, put x2 to be 1. So we have two eigenvectors, minus 1 and 1, 1 and 1. And clearly, if you look at these two eigenvectors, you put them in a matrix P, 1, 1, minus 1, 1. What do? We just want to prove that diagonalizes A. That means I want to find a matrix which is diagonalizing. That means that matrix, when multiplied, that means we're trying to say is A is diagonalizable. That means I'm able to find a diagonal matrix D such that D is P inverse AP. That's what I'm simply saying. Because if I want to find a matrix that diagonalizes, that means can I find a diagonal matrix D that is similar to A? That simply says D is P inverse AP, or PD equals AP. P. That's what we have to prove. That if I say find the matrix which diagonalizes A, get the eigenvalues, get the corresponding eigenvectors, and then just simply do this little matrix multiplication and prove that they are equal. And that's what we do. We check B times D, we get this matrix. We do A times B, we get this matrix. Clearly, A is diagonalizable. Now, this is simply proving something is diagonalizable by the virtue of what we have to go through, like finding eigenvalues, eigenvectors, then we just do this matrix multiplication. Okay, now we're going to look at a very important fact is how do we diagonalize a matrix? So these are the basic steps, guys. You find the eigenvalues of the matrix. You find the eigenvectors of A which correspond to this matrix and they are linearly independent. Then construct this invertible matrix from these linearly independent eigenvectors. Then construct the diagonal matrix from the eigenvalues of A and then simply check the answer. What does the check the answer means? P times D equals A times P. That's what simply it means. So let's look at a 3 by 3 matrix. And we would like to diagonalize this matrix A or find a P which diagonalizes A. So that's how the questions are. Now this again is a matrix which I had done earlier in section 5-2. And you just need to go back and look at those notes. We found that the lambda was 10, 1, and 1. One of the eigenvectors which correspond to lambda equal to 10 was this. Remember, eigenvectors corresponding to lambda equal to 10 were. It was x1, 2, 2, 1. Just put x1 to be 1. That's it. For lambda equal to 1, remember for this one we had x1, 1, 0, minus 2. Because remember, it was a linear combination of all possible of these vectors 1, 0, minus 2 and 0, 1, minus 2. This is for lambda equals 1. What did we do? Put x1 to be 1 and x2 to be 1. So these are eigenvectors. So these are the ones which form the eigenvectors, guys. We need just one of each. And remember also the theory which says if you have A is diagonalizable if it has 3 distinct eigenvectors. So when we put this vector from lambda equals 10 and these 2 vectors from lambda equals 1, this automatically says A is diagonalizable. But here we want to prove that. We want to find P that diagonalizes A. So once we have found our eigenvalues, eigenvectors corresponding to that, now how do we write? This is very important, guys. The writing of the D's and the P's. Remember, the D will be eigenvalues over here. So 10, so the convention is the first eigenvalue will correspond to the first eigenvector. The second eigenvalue is 0, 1, 0. It can be this or this. It does not matter. So this is 0, 1, 0 and this is 0, 0, 1. Both of them are coming from lambda equals 1. And then what we do is we just simply check B times D and A times B. Both of them are basically the same. And hence, we have been able to find this P that diagonalizes the matrix A. Okay. Very important, another theorem related to diagonalizable. If A is, this is naming it a theorem B, guys. If A is an n cross n matrix with n distinct eigenvalues, then A is also diagonalizable. The question is every matrix diagonalizable? Nope. So let's look at this one. That if I have a matrix this. Now this is a nice little matrix. It is a triangular matrix. And if you notice, the eigenvalues are already on the main diagonal. And each one of them is distinct. By applying this theory, we say, hey, A is diagonalizable. We don't have to do anything. So thus, by theorem B is diagonalizable. Very simple. But remember, in general, not every square matrix, okay? In general, not every square matrix is diagonalizable. So we are done with this section. And here are the set of questions, guys. I want you to practice from the book. 1, 2, 5, 7, 9, 11, 13. Thank you.